Okay, let's start today's lesson with a demonstration that we'll refer back to as we go throughout it, okay? So as always, we want to make sure, as we're learning our topic, that we connect all three sides of our chemistry triangle, okay? So what do we see with our eyes? So we'll do a demo so you can have something to see. But then, visualizing what's going on at the molecular level. And then the big part of today is learning about how to write it symbolically. Okay, so by the end of today, our goal is I can write and visualize what are called net ionic equations. That's all the assignment is and all the practice, just writing net ionic equations. Okay, so by definition, let's start off with a type of reaction. Now, we will be writing net ionic equations for other types, but here's one that's very common. They're known as precipitation reactions. Okay, another name they're often called by because the pattern is a double replacement reaction. And they always have a similar type pattern, okay? And by the way, we're going to skip around just a little bit in our notes here for a second to help it match with our demo. So flip your page over to page 10, and we're going to draw a picture at the molecular level here real quick. Okay, so I have here in this flask a 0.1 molar potassium iodide solution. Can someone by raise a hand just remind us what do I mean when I say 0.1 molar? What does that mean, Mary?
It means that there's 0.1 moles of your solvent in your solution.
Perfect. In a liter of solution. Good. Have a nice face, right? So potassium iodide is a solid. It's like a white powdery thing, as many ionics are. Okay. I measured out 0.1 moles because I figured out its molar mass. I put a little bit of water in here first so it wouldn't get stuck to the bottom. Then I put in water. Then these right here are called volumetric flask. And they are designed to measure a very accurate volume, but only one measurement is what it does. So I'll bring it around really quick, and there's a very faint silvery gray line on it. So it only has one marking because it's only designed to measure a liter, and that's it. But it's the most accurate way we have of measuring a liter. So if I fill it exactly to this little gray line, then that is exactly a liter plus or minus 0.3 of a milliliter is my variance. If I use a beaker or an Erlenmeyer, they are not as accurate.
Because this thing goes so narrow so quick.
Yep, the narrowness of it. Now you can buy, so I should have brought a few in. I have varying sizes of volumetric flasks, right? Like I have like little tiny ones and bigger ones. Once again, they're used to make solutions because you want to be as accurate as possible when you're trying to make a set molarity. Okay? All right, now, yeah, go ahead, Mary.
So how do you know that the molarity of that, if it's not all the way up to the liter point?
It's because I already poured some out. So when I made it, it was to that line.
Oh, okay.
Does that make sense? So, but obviously, if I didn't, it wouldn't be. So, yeah, let's see. Good question. So because molarity is a ratio of moles per liter, even when some is gone, the ratio is maintained. Yes, there's less liters and there's less moles, but since they both went down, the ratio is maintained. Yeah, good question though.
So how does that, why does that work better than other tubes?
Because the narrowness of it gives you the accuracy of your measurement.
But like, graduated cylinders are also narrow.
True.
It would take up the graduate.
To get a liter, to get a graduated cylinder that was this narrow, to get it to be a liter would have to be like this tall from the floor.
Okay.
Does that make sense? So I have like some 500 milliliter graduated cylinders, and they're probably about that wide.
Oh.
Does that make sense? And they're about this tall already.
Wow.
So does that make sense? Yeah, good observation though. Miriam.
So you said that you have like really small ones of those?
Mm-hmm.
How on earth do you fit a liter in those?
So the idea, once again, is it's a ratio, right? And so you can still make a molarity. You just would calculate how many moles per 200 mils, right? Obviously, you wouldn't. It's not a liter anymore. So now, with our example here, okay, Ki as a solution, right? So in our equation, I'm going to highlight it up here. We're going to draw what this actually looks like if we could magic school bus inside, okay? What's going on? I'm going to put it in, I guess I'll match it up to my equation. So I'll put it in this box right here, okay? Just so you can see which is in which, okay? When, reminding back from Unit 3, when an ionic substance is dissolved in water, Show me with your hands what is happening to our ions. Show me with your hands. What's happened to the ion? Make up some sign language here. And I'll pick my favorite one. Okay, Hadley, I think I like yours the best. Will you show us what you did? They're breaking apart. Some of you kind of did that, but you had sprinkly fingers, and I didn't know what that meant. Okay, but the ions break apart because, remember our little Mickey Mouse's waters attach to the positive and negatives and pull it apart. So that's what we're going to draw in this first box here, or the second box, is the K and the I are no longer together, right? It's not existing as Ki anymore, but it's actually K plus and I minus. Now I am going to maintain the balance of our equation, otherwise it wouldn't work. So I am going to put 2 of them in there. Once again, could I have more than 2? Yeah, but we have to have at least the minimum, otherwise it won't work, right? So we're going to draw the minimum needed. Okay, all right, in my second box, I have my other flask. So this flask right here has a 0.1 solution of lead nitrate, lead 2 nitrate by its name. Okay, so let's draw a picture of what that looks like at the molecular level. So when this substance right here, when this dissolves, remember the metal breaks off because that's the positive side. So we get Pb 2 plus. And then the nitrate, remember our polyatomics stay as their grouping because they are covalently bonded together. So the water doesn't break those apart from each other. Hopefully this is ringing a bell back from Unit 3. Questions on anything I've drawn so far? Yeah, Will.
It wasn't about what you drew, but how do you know the lead 2 plus?
Oh, the charge of it?
Well, not the 2 plus, but how you're talking about how it was lead 2.
Oh, that will be told to you in the problem, because otherwise you wouldn't know. Yeah.
So you can't just tell by the equation?
You can kind of, if you work backwards, which we'll do in a second. So I guess there kind of is a way to tell.
I kind of need a review on it.
But yeah, we'll go over that in more detail. So determining the charges, we'll go into more detail in just a minute. But Eddie, question?
Was that what you just said, that we'll figure out the 2 plus?
Where that came from? Yeah, we'll go into that in a little bit more. Okay, so I'm going to pour some into some beakers. Then we're simply going to pour them together. Now once again, I don't care too much how much I have. As long as we have enough of both, right? It's okay if there's excess floating around in there. Now don't say anything out loud, but looking at the balanced chemical equation in your head, don't say it out loud, make a prediction of what you think you're going to see when I pour these 2 things together. Look at the equation. What prediction can you make before I do it? Don't say it, but just think it. Okay, whisper to your table buddy what you think might happen, and then we'll try it. Okay, ready? Okay. Everybody ready? Don't blink. 3, 2, 1.
Oh,
Orange juice. Just kidding. It's not.
you do not want to drink that.
Yeah, that's if your orange juice is that color, you should not drink that either. Okay,
Like orange juice flavored medicine. That's what that is.
What?
Steven.
That was so dirty.
Can we shake it?
This and this.
Yeah.
Just like
It would work. It just would contaminate my whole
Can we put
sample.
the ends together? Can we tape the ends together and just like shake it back and forth like the weirdest dumbbell ever?
Just like make it all together. No, because I don't want to have to make more solution. But. Yes, AJ.
Did it create any heat or get colder?
Not that's measurable by touch. So measurably by touch, I don't notice anything there. But good question. Will.
Could we change it back to clear somehow?
It's a chemical change.
Well, yeah, but like if not like separate it, but add another thing to make it clear.
If you add enough water, you can tell.
Not that I can think of off the top of my head. Yes, Leslie.
Why exactly did it change to that like neon yellow?
Yeah, it's such a bright.
It's very bright. Now I don't know if I have a best answer, but we can kind of answer it. Mary.
What happens if we just put a tiny bit of the first solution
Oh, yeah.
in the second one?
as long as at the molecular level you have 2 of these for every one of those, you'll get a change. So even drops of them would make a change.
No, but like,
Would
what
it
if you just
be,
had,
like,
a lot of
tinted?
one and a tapered the
You
other?
would still get some reaction, but obviously as soon as you run out, then it wouldn't make more, right?
You should show us.
Maybe when we're working later, remind me and I'll go grab a pipette and we can drop some in and see it just like form by drops. Is that what you're kind of saying?
Can we see this reaction but on like a large scale and in slow motion?
I'll work on that. So notice this, everybody, with our balanced equation. Okay? What does our balanced equation say we're making? A solid, right? Now, what's interesting is,
Wait, does the solid combine with the?
where's our solid?
It's a solid.
It's just kind of round.
Yeah.
You can see it. No, no,
No, it's probably not.
Someone say it's a powder. So I'm going to show you what the one from last period. So as it sits and settles, the powder will start falling to the bottom. So that was last period, and then this one was the one I did this morning. Right? So the powder will eventually settle down to the bottom, and then using filtration, I can get it out, and I'll come show you what it looks like.
Wait,
So-
could you just like use a magnet or something? Because lead is magnetic.
But is it just lead?
Well, like, because they was glued to it.
Lead iodine.
So this right here is our lead to iodine.
It looks like curry powder.
That's so weird.
How does it change?
Wait, why does lead make?
Because aren't they like white
Lead is metallic.
Lead is so.
And iodine is a white substance.
Color theory doesn't prove that.
It's not color theory, it's a chemical change. That's exactly how you know that.
Lead and paint.
What in them changes the color?
I didn't experiment.
How does that change the color?
Putting lead in
In the mouth. Not like. Not like this.
Okay, so let's draw our picture here of the end. Okay?
Just makes sense.
So in our end beaker, first thing we're going to draw, that's our solid. We're going to just show it as a clump at the bottom. I am going to label it, right? So this is my P, B, oh, that should not be capital. That's what is on my mind, I guess. PB, I2, that's our solid. Okay?
That's why it's yellow.
Notice, though, everybody, look at our before. Matter cannot be created or destroyed. What still needs to be floating around in the water that we can't see? Good. So we still have potassium. What else? Good. And our NO3, our nitrate ion. Right? So these ended up, what we would say, not reacting. And they're still just floating around. Right? Because they didn't come together to make something new. Right? They still are just floating around. Yes, AJ?
If lead and iodine are both ions, what made them react?
So what's interesting with the precipitation reaction is the forces pulling these two together are stronger than the ion dipole forces of the water. And so that's what actually keeps it. So there actually are certain ionic substances that are not soluble and they don't get pulled apart by the water. So, yes, Mary.
Would it be safe to drink that water after?
It's not water, it's.
It's potassium nitrate water, so I wouldn't recommend it.
I mean,
Well, like what would happen?
I mean, potassium would be fine. The nitrate side of things, I don't know. I don't know what nitrate does to you, but it's not something we ingest on a normal basis. That's nitrogen. It's different than nitrate. Okay, ready? I got a question for all of you. What do you call a person who watches a game but doesn't participate in the game?
Me.
Michelle.
Boring.
Boring.
party band.
Spectators.
Oh.
These ions that aren't doing anything in the reaction, right? They're floating around on the left. They're still floating around on the right. These are called spectator ions. Okay? Now, this picture right here is known as the complete equation. It's showing everything that is present, and we can actually write it as a balanced chemical equation. So that's what we're going to do in that first box, right underneath there. Okay, I'm just going to translate this into an equation. Okay, so I have Pb plus 2 separate from 2 NO3s. Once again, so we're showing them in their true state. We then have 2 K pluses and 2 I minuses to make PbI2 as a solid. Notice that one does not have charges because it's a solid, right? They're not broken apart into their ions. But then we still have our 2 K pluses and our 2 NO3 minuses. So once again, this is just our visual in a chemical equation form. This helps us see what I like to think of as the true state of everything present. Because even though the overall reaction has it written as Ki, since it's aqueous, it's not really Ki. It's really K plus I, right? They're separate from each other. The net ionic equation, which is our final step here, simplifies a reaction to just show you what actually played the game, and you get rid of the spectators. So if I get rid of the spectators, my net, I'm going to keep that like there just so we can see it. My net ionic equation would be, we made PbI2 from Pb2 plus and 2 I minuses. So I'll highlight up here. You could almost think about, once again, like we're canceling out the spectators because on the left they're just floating around and on the right didn't change, no new bonds, it's still just floating around. And the net ionic equation is what we get when you take those things out. Yeah, Will?
Is the difference between aqueous and liquid just that they're not combined in the same substance?
Aqueous means it's dissolved in water. Liquid would mean you melted the substance. So like aqueous NaCl is salt water. If I said liquid NaCl, that's like me melting salt on a hot plate and turning it into a liquid. Does that make sense, the difference?
Well, but then why is, on each side of the equation, like Ki, why isn't that one element, why is that K and I don't know how to explain that.
Another thing maybe what you're asking is aqueous substances as ionics always break apart. So if it's aqueous, it's always going to be shown as separate ions. Is that kind of what you're saying? Nope.
Oh, okay. Yep, that's what I
Yeah. Yep. Unless it's covalent, but like we won't be looking at ionics for now. So yes, Cameron.
Okay, this is kind of a dumb question, but is there ever a point in this class where we would be able to do baking soda and vinegar experiment and have it be part of a legitimate lesson?
Just for fun.
No, as part of a lesson. Did you not hear her?
Oh, as part of a lesson. I'll be honest, I don't typically use them because I like to use things you guys can't buy to do demonstrations.
You have a point.
Because you can do that at home. You can't do this at home. Right? Like, I mix baking soda and vinegar at home all the time, don't you? Do other people not do that on a daily basis? Just kidding, I don't do it on a daily basis. But I will think of maybe a way we could bring it in if you want.
This is like the classics of chemistry.
It
Like, especially
is.
with science.
I just, Timmy, once again, I like to do things you can't buy. Yes, Leslie?
Why didn't NO3 and K combine?
The force between those two is weaker than the force of the water pulling them apart. And so they just get pulled apart. Yep, the water.
Like, what if it's like it was maybe like a different solution or like the
Possibly. Yeah, possibly. Yeah. Yes, Miriam.
This is kind of just a question of like notation. When you're doing like things with iodine mostly, should you always write the uppercase I with the like top and bottom bit? Because it always is so confusing to me
know.
when it's like carbon and
It's not really a universal thing to do. Like,
Like,
I
but
do
why?
it. It should be. Because I have so many people who always get confused of, is that chlorine or is it carbon and iodine? It should be universal, but it's not. So you don't have to. I do, because I guess maybe for that reason, but. I would say never assume carbon and iodine. Always assume chlorine.
Like if we can't tell, we just like have to squint at it and try to.
Just, it's always chlorine. I don't know. I know, because even like my one up there, right, is not that font, right? So. Always assume it's chlorine, never assume it's carbon and iodine. There's no compound that is just straight, like, you could have like technically like carbon and iodine 4 or something, but once again, it's like, there's just more, I don't know, I don't have a good answer. It's just your odds are better to pick chlorine. Pick chlorine. So, okay, we're going to go back now. So flip back in your notes to page 9. Okay, and let's kind of go off of what Leslie brought up. So Leslie brought up, and AJ did as well, about this idea of like, well, why did those two stay together, right, and the other two not? So it's all about the forces that are holding them together. And scientists, once again, you guys live in a time where they've done zillions of experiments, and they already know what things will always stay together, and what things will sometimes stay together, and what things will never stay together. And they have come up with the rules of solubility. So one big thing, definition to remember, is if it's soluble, that means it is breaking apart. Okay, sometimes students accidentally get it backwards because they think, oh, soluble starts with an S, and so S is the solid. But soluble means it will break apart. If it's insoluble, right, so things that are insoluble mean they are forming the solid. Right, that means they are not dissolving. Go ahead, AJ.
I was wondering if we threw our powder into hydrochloric acid with it.
It doesn't dissolve in hydrochloric. We tried that last period.
What about hydrofluoric?
I don't know if it would. I'm not sure. I don't have any hydrofluoric on hand, though, to test your theory. I'm not sure. I'll think about it. Yes, Miriam?
Why is it that we always, why is it that water is the standard for solubility? Like, is it just because we have a ton of it? Like, are there separate rules for dissolving things into different things?
Yeah, technically these rules only apply when we're dealing with water. It's considered the universal solvent, and so that's kind of why. But yeah, technically you are right. These would not apply if you were trying to dissolve it in something else, per se. So yeah. Now, with these rules, we do not have to have them memorized for the AP exam. That's one thing they state out very clearly, except for just 4 pieces. So down below, I've put them emphasized here. I want you to highlight this box or put a big star right here. This we do need to have memorized. The rest of it, we'll have the table as reference, or they'll give you some other information. When you look at a compound, if it has one of these 4 things, I'm going to write their symbols if that helps you instead of their names. So if it has Na in it, if it has potassium in it, which is K, if it has ammonium, which is one of our polyatomics of NH4+, and then nitrate is NO3-, if it has one of those in there, it's always aqueous, meaning it's breaking apart. If it doesn't have one of these, then the default is to assume it's the precipitant. Okay, so the precipitant is the other name we give the solid that got made, because it precipitated out of the solutions. Okay?
So does that mean that they're always spectators?
Yes. Yeah, good, another great way of saying it, Rachel. These will always be spectators every time. Yeah, have a smiley face for that. All right, let's practice writing the products when it's not given. Okay, so on our example problem, just to help us see, I said, okay, I'm going to mix these, and it's going to make these 2 products. Our next step now is being able to predict what's being made based off what is shown. So step number 1, I'm going to use different colors once again very strategically in my thought process. So if you want to highlight as well to remind yourself of your different steps. Okay, so my first step is I know I'm mixing MgNO3 and NaOH. Right, so they'll tell you what you're mixing together. Our goal is to figure out what is being made and which one is the precipitant. And then our next step will be to write the net ionic equation. Okay? All right, so my first step I'm going to do in red here. Oh, not delete, red. Okay, is you need to figure out, because both these things are aqueous. I forgot to label that here. Your reactants always will be, because otherwise you can't really have much of a reaction if you don't start with aqueous solutions mixed together. So, since they are aqueous, how is this really existing? Is it together or apart? Apart. So we need to identify the different parts that are floating around and their individual charges. So everybody find magnesium on the periodic table and put your finger on it. Find magnesium. When something is just an element, reminder back from Unit 2, its charge is based on how many valence electrons it wants to give away. So magnesium's charge would be a +2 charge, because it has 2 valence, and so it wants to give those 2 away. So write the charge, everybody, above magnesium there. Okay? Now, when you have one of your polyatomics, the way to figure out their charges is to balance the molecule. So since magnesium here has a +2 charge, and notice in my molecule I have 2 of them, each individual nitrate must be -1. Give me a thumbs up if that makes sense. Give me a thumbs down if that doesn't. I'll say it a different way. So the molecule as a whole needs to be 0. I know this one is +2. I have 2 of these things floating around, so individually they're both a -1. The charge should be by individual basis, not by like the sum. Give me a thumbs up if that made sense. Let's make sure we're all thumbs up now. Yeah, Stephen.
And you know it's +2 because the NO3, there's 2 of those.
Yes. Yeah. Any other questions? Yeah, let's see.
Basically, they just want to be unequal.
Exactly, because that's why they're going to form a bond is to be balanced. So, okay, find sodium on the periodic table, everybody. Find sodium. Turn to your neighbor and tell him its charge. If you told your neighbor +1, have a smiley face. Okay. Now, OH is another one of our grouped elements, right? Once again, if it helps you, you can always throw parentheses around them to remind you, like, hey, this is in a group, okay? And its charge would be -1. Questions on identifying the charges? Okay, step 2, I'm going to change colors, is trade partners and write the new products. So a double replacement is a little bit of a do-si-do of I'm going to trade who I'm dancing with. So magnesium is positively charged. So it's going to find the negative in the other molecule. And then same thing, this positive will connect with this negative. That turned out so cute. It actually looks like a snowman.
That is not elephant toothpaste.
That turned out really well. I don't know why it formed like that. Wow. In general chemistry right now, we're learning about synthetic compounds and things. And so this is a...
Can you do that?
Can I do this for you?
Yeah.
I can do it at the end if you want, just for fun. But it starts as 2 liquids, and then you pour them together, and it bubbles up, and then it hardens.
Is it not like foam then? Is it like hard?
It's pretty... I mean, it's some... I don't know.
Like, could you break it with your hands?
Yeah, you could break it, yeah, if you wanted to, but...
That'd be kind of...
But I think she was showing me because it, like, poured out so, like, snowman-like, you know? Like, why to do that? I don't know.
It's Christmas.
It's a sign.
Spirit of Christmas.
Okay, coming back up to net ionic equations here, everybody. Okay, look at this, everybody. Eyes up here. Show me your eyes. So magnesium is now pairing up with hydroxide, OH. When they form a new relationship, you have to rebalance their charges. So magnesium's coming with +2. Hydroxide is coming with -1. So my end formula is MgOH2 because it has to still be balanced. Okay? Okay? So then our other compound, not this one, everybody. So now sodium plus 1 bonding with nitrate, NO3, which is minus 1. So its formula would be NaNO3. Because it was a plus 1, minus 1. Yeah, let's see.
What's the excess NO3?
As far as I know.
Good question. Now, here's our final step. We do need to make sure that the whole equation is still balanced. So this just goes back to balancing like we've done. So if you want, you could build your scoreboard. I'm just going to look at it and say, okay, I made 2 of these, which means I should have had started with 2 of them. So I'm going to put 2 out front there. So put your big numbers in front at the end, which means there also should have been a 2 right there. So just like we did with normal balancing, but that should be your final step. The biggest mistake I want to emphasize so you don't make it, small numbers on the left don't get carried over as small numbers on the right. Because small numbers are there to indicate the bonding relationship. Right? It was here because of this relationship. It's now in a new relationship, so you have to reevaluate the subscripts. Questions on step 3? Final step 4 is identify our precipitant.
No.
Which one's it going to be? This one. How do I know, Rachel? These are in our group of 4 that they're always spectators, so it can't be that one. Kind of process of elimination. So I know this one's going to be aqueous, and this would be my solid. Questions on that before we try another one? A little bit faster. Okay, turn to page 11, everybody, and let's do another one. All right, I'm going to do one more with you a little bit faster just to make sure we don't have any confusion, and then I'll have you try one with your table, okay? Turn to page 11 here, and we'll go through our steps. I know, I was reviewing my lesson this morning, and I just had an epiphany of it would go better in this order, and you already have papers, so. Okay, BaCl2. Reacting with K2SO4. Okay, so we're going to start by writing what's given. Step number 1 after writing what's given is identify individual charges. Okay, so I'm doing that in red here. Find barium on the periodic table. Barium's going to have a 2+ charge. It's paired with chlorine, which would be -1 or 1- charge. Doesn't really matter. Okay, got a potassium, which is a +1. And it's paired with sulfate, SO4. But notice you have 2 Ks. So that means sulfate must be 2- or -2. I'm going to keep that uniform here. Okay. Questions so far? Yeah, Marilyn. It's like each of them individually. So the charges should be individual charge, right? So each of them individually is a -1 charge. So we know potassium is +1, but since I have 2 of them, For it to be 0, that has to be a minus 2. Does that make sense? Yeah, good question. Okay, step 2 I'm doing in blue. Okay, step 2 is to trade partners and rebalance charges. Okay, so we're trading partners. Once again, I poured them together and the positive and negatives can find each other, but we have to rebalance the new charges, okay? So barium pairs up with sulfate, and look, how convenient. +2, -2, so it's just BaSO4, because you only need one of each to make them both happy. Then, K is bonding with Cl, and they are +1, -1, happy couple there, KCl. Questions on step 2? Okay, step 3 is balance the overall reaction. So I noticed that I had 2 over here, so we need to make sure we ended with 2, which works out because our chlorine also needed it. So that's the only balancing needed to be done. Okay, and then step 4 is identify our precipitate. Who's it going to be? Yeah, yep, so our bariums are solid because this one has potassium, and so it must be the spectators.
So if it includes potassium at all?
Yep, it doesn't have to have both. It just, if one half of it is one of those, then the whole thing will be.
What if potassium was bonded with something else, which was its own thing, that was then bonded to chlorophyll? Like, would that change anything?
I'm not sure.
Say instead of BaSO4, what
Yeah.
if it was BaKO4 if that existed?
It doesn't, and it never will.
Yeah, but like something similar.
So none of them do, but I see what you're asking, Will. So metals don't exist as polyatomics. So you'll never have K bonded with something else. So good question, though. I see what you're asking. Okay, any other questions? Yeah.
What if neither of them has one of the 4? Like, if the
Ooh, that's a good question.
Does it just turn into a solid then?
So what Miriam asked everybody, listen up to this, is she said, what if neither of the 2 have, our 4 always spectators?
it's like lithium instead of potassium.
If it were on the AP exam, they would give you some information to help you know what the spectator was. I don't know exactly what that would be, but they'd give you something. For your homework, you can then reference this rules chart to figure out if it's soluble or not. So, does that answer what you're
Will
asking?
they ever give us something where, like, they're both spectators that literally just doesn't actually do anything?
Yes, and that's where you would say no reaction occurs. Yep, if both of them end up being spectators, then you pour 2 things together and nothing happened. Which you might find next time when we do the lab. Because next time you're going to do like 20 different combinations and seeing which ones happen and which ones don't. Yes, Stephen?
Why is it 2 KCl instead of just KCl?
So the big numbers are to balance out, right? Because matter can't be created or destroyed. And so if I started with BaCl2, I can't end with just 1 Cl. And so when they get made, it's creating 2 potassium chlorides.
Okay.
So, does that make sense?
Yeah.
All right, now with the net ionic equation, what do we get rid of in the net ionic? Who's not included? Who's not playing the game?
KCl.
Good, K and Cl. So my net ionic is going to get rid of those spectators. So I would just have Ba2 plus, Cl's a spectator, so I'm going to ignore it, plus K's a spectator, take that away, SO4 2 minus to make BaSO4. So your net ionic should just show the things that are used to make the precipitant. Questions on that before I have you try the next one for a smiley?
Wait,
Yeah.
how do you know which one's the net ionic?
So you focus on the precipitant. So this you keep, and then whatever ions are needed to make that.
Well, how do you know which one it is?
Oh, that's the solubility rule. So you look for if it has any of these in it, it can't be the precipitant.
I can't do it.
And so since, let me scroll back here, since KCl has K in it, right? We know that can't be the precipitant ever.
Okay. Oh, and that's what the AP test gives you. So
Yeah, they'll give you, like those four you have to memorize. You do have to memorize the four I told you, but if it's something besides those, they'll give it to you. Okay, try exercise 4.2b with your table. Once you think you've got it, you need the overall and the net. Raise your hand and I'll come check you off for a smiley face, okay? Let's shoot for 5 minutes here. Once again, when you're learning something new, remember, take it slow brain. Eventually you can go fast brain, but take it slow, right? Go through step 1. What are the charges? Balance those charges. Good job, Grayson. Have a smiley face. What's the charge of calcium?
Oh wait, brain, silly brain.
There you go. Good catch.
There you go.
Good. Have a smiley face. Good job, Layla.
I was like, oh yes, it's positive. I completely missed the fact that I also need to be very positive.
How much positive? That's a good way of saying it. Once again, take it step by step.
It's 2 minus though, because the NA has.
Once I check you off while you're just waiting, you can welcome to start on some of the homework questions, which are just like this. We have one more we'll do together, but you can try the first few while you're waiting for everyone to get checked off.
Do you have tissues somewhere?
Yeah, they're right over there by the pencil sharpener. Yes. Yes. Remember, I don't know if it truly matters, but label that as solid.
Oh yes.
But,
So,
yes,
sorry,
good job,
I labeled it in the first part, but I forgot to.
Oh, gotcha. Did you have a question? Oh, okay. Ready, Gavin? Okay. I have a tickle in my throat. Once again, once you think you've got it, raise your hand and I'll come check you off.
No, yeah, it's sodium.
Well done. Good. Have a smiley face. So the net, you're. Let me see when we're. Okay. Come up here really quick. Do you remember how you got a -1 for CO3?
Wouldn't it be -1 because this is plus
Ooh,
1?
look at the compound that's given. You had 2 NAs in the compound, so what would CO3 be?
That would be -2.
There you go. So then, so carry that down over here now. So if it's Ca2 plus and CO3 2 minus,
Wouldn't need.
there you go. Yep. So then it's just, yep, CaCO3. Good. Now you do show charges, so the net should show reactants and product. The reactants should show their charges, because that's how they are. But then the charges are gone once it's a compound. So, yep, good job, Trip. Have a smiley face. Yes, good job, Michael. Have a smiley face. Good first step. So now, figure out which one's your precipitant. And then get rid of the spectators.
Okay, I think Eddie. Is that not right?
It looks minor on here, but in actuality, it is different. Why do I need a plus sign between them?
Oh, because then they go.
Good, because before the reaction, they're not together. Right, and then after the reaction, they're together. So yes. Good job. Have smiley faces.
We're good, Eddie.
Good job, Maddie. Have a smiley face.
I've been keeping track. I remember I went through my notebook.
Perfect. What's on the other side of the arrow, though, for your net?
Yes.
So what is being used to make this?
All these
You tell me. So looking on this side.
2 more minutes until.
Is that whole thing being used to make this? What part of it?
My house. Just the.
Good. So write Ca2 plus.
Filter your house with.
And then we're not going to write Cl because that's a spectator. Do we do Na or is that a spectator? Good. So don't write that. but then write CO3, CO3 2 minus. There you go, good, have a smiley face. Well done, have a smiley. Good job. Do an arrow, not an equal sign. But yes, I know what you mean. Have a smiley face. Oh, I already checked you guys off. Great, let's take a look here.
They also finished and need theirs checked off.
Perfect. Okay, that looks great. Are they the same? Did you compare?
I believe so.
Yes, good job. Have a smiley face. How are we doing over here?
Hopefully good.
Super good. Have a smiley
Yay.
face. Good job. Yes, well done. Good, have a smiley face. Oh, it's coming off.
Steven, you broke it.
Good job. Have a smiley face. Mason. Minor but important detail. When they're separate, you have to show their charges.
Oh.
Because there is a difference between just calcium versus calcium, right? To show like these are the ions floating around. There you go. Yep, good job. Quick, seeing how you doing?
I'm so confused.
Close, close. One thing about like the splitting. There's a pencil here that's a different color.
I remember I've learned about it.
So like with this compound here, when you think of it like, oh, this is actually better. Do you remember why? So it should have the 3 still. Because this is kind of like one of those grouped elements that just stays as its group. But then that would be better. So then you would have this as your product, and then the reactants, the left side of it, should show what is making this. So we wouldn't really show charges anymore there, but you would show them on that side of the arrow to say this piece and this piece are making this one. Does that kind of make sense? That's the idea of the net ionic. It's like, yes, everything is here, but what's really happening is just this. Does that help a little bit? Okay, we'll keep practicing. Okay, is there anyone I didn't get to? Leah? Yes, well done. Have a smile. Okay. One last thing here. You know, right when you all feel confident, you know what you're doing, I have to show you when it gets weird.
Oh, no, but it makes sense.
Okay, go down to this very last one in your notes. Okay?
How to make it not make sense.
It's not me. I didn't make up chemistry. I just teach it to you, remember?
Make chemistry simple.
Okay.
Actually, I'd rather it not be simple, because then they'll be incorrect.
When you come across everybody, what is called not a double replacement. I put unique, but the way to look at it is it's not a double replacement. So double replacements are like all the examples we've seen so far where you have 2 things here, they switch partners to the other side, okay? If it's not a double replacement, the process is still the same, but what we're gonna find is it doesn't simplify as nice, okay? So we're gonna do the same thing, you'll see why it doesn't simplify as nice as before, okay? So my first thing I'm gonna do is I'm gonna write the whole complete reaction. So we're gonna write everything in its visual, actual form, okay? Go as far to the left as you can because we gotta write a lot of stuff here, okay? So, since this one here, everybody, is aqueous, it exists as 2 separate pieces. So we're gonna write it as Mg2 plus and S2O3, which would have a -2 charge, because if magnesium was +2, the thing it's attached to must be -2. Okay? So there's our first compound. All right, next one. We got another Mg2 plus. It's paired with an OCl. And since there's 2 of them here, I'm going to put a 2 out in front, and each of them has a -1 charge. So once again, I'm just going through like we did before and identifying all the individual charges.
Wait, is that that chlorine or is that iodine?
Chlorine.
Okay, cool.
Like I said, always assume chlorine. Good question though. Okay, next one. Drawing this compound, we got another magnesium, 2+ charge. Now we got 2 OHs, each with a -1. So I'm just breaking down all the aqueous substances into their individual pieces. All right, it's a big puzzle, break it apart. All right, drawing my arrow. Got another magnesium. Now notice if there's a number in front, keep that with it, right, to maintain the balance. And then we're going to have 2 SO3 2 minuses. I'm going to run out of room. Hopefully you didn't. Oh, you tiny writers. Good job. All right, we're going MgCl. I'm going to just write it below. So we got Mg2+ and 2 Cl minuses. Once again, I'm just taking the compounds, breaking them apart, except which one's not going to break apart? Water, because is water aqueous?
Wait, it is water. Isn't water always aqueous? It says it's liquid.
I know, it's like going back to, is water wet idea, but this is the scientific way of asking it. Water is not aqueous. It doesn't break apart into ions and, well, okay, we'll talk about that actually in Unit 8 later on, but it just stays as a liquid, okay? Okay, any questions so far? Yes, Will?
Why is SO3 2 minus?
Because it was paired with magnesium, which was a +2 charge, right? So it came from this guy. And so to be balanced, it had to be 2 minus.
Oh, because the 2's in front of all of it.
Yes, the big 2 in front is impacting the whole thing. So, okay, any other questions before we do our next step? Okay, now once again, this problem, everybody, give me your attention. It looks different, but it really is still the same steps. We're looking at all of them as their ions, and now we need to get rid of the spectators. So who is spectating this reaction that I can get rid of? Good. Now notice you have magnesium in a lot of places, so make sure you have the same amount. So the left side has 1, 2, 3, and the right side has 1, 2, 3. So they can all cancel away. So magnesium is spectating this party. Because it's on the left, it's just floating around, and on the right, still just floating around. Any other spectators people see? On this side, it's OCl, but on that side is actually now just Cl. So that actually is a change, but good observation, Mason. Good, so this is S2O3 is not the same thing as SO3. Those aren't the same thing, so we can't cancel those out. And we have no other spectators. So my net ionic equation
Oh my gosh.
is everything we didn't cross out. So it's S2O3 2 minus plus 2 OCl minuses plus 2 OH minus, creating 2 SO3 2 minus, 2 Cl minus, and H2O liquid. So sometimes, right, there can be things that don't appear to be making the end goal, right, like H2O, but somehow all these pieces played a role in making this be. And so we don't get rid of them. Yes, AJ? Say that again. Because you're just making water? I don't know. Yeah. But it's just aqueous solutions making more water.
stuff dissolved in water. And you just create.
And then we're making more water.
Just take salt water and then you get slightly less salty water.
Yeah. I don't know if you would actually observe any sort of. I don't know. That's a good question, though. Any other questions with our kind of weird net ionic equations? Yeah, Miriam.
How weird would it be to figure out the molarity after this? The water as the product from the product. That was part of the product.
Yeah, that would be very weird because now, yeah, that would be very hard to do. Well, there'd be a difference. You could do it stoichiometrically and it wouldn't be too hard. But in actuality, like to actually physically measure it out in the lab, that would be very difficult.
Like which water?
Which one came from which?
What
No.
molarity of water is in this water?
Well, yeah, I don't know.
From this, you could figure out the
You
water
could.
molarity.
Well, water doesn't really have a molarity, but
Well, how many moles of water are in this water?
are in this. How many moles of the new water
Yes.
are in the old water? Is that what you want to find?
Yeah.
Yeah, you could. Yeah, you could.
What is the molarity of the new water?
Okay, really quickly, everybody. You got 6 minutes. Homework tonight is 4.2. You can't walk out my door until you have one problem done on your homework. I'm holding you hostage until you have it done. You gotta have at least one problem done. The other way, Leslie, is the first thing listed is always the You'll like see it again down I guess I can stop my recording.